Hello, in this example, we are going to see how to design functions using decoders. So the example 2 is already solved in these slides. And the idea is very simple because decoders implement all the minterms or maxterms of a function. If we express a function as a sum of minterms or a product of maxterms, we can just use a decoder and a single gate to make this the sum, it's the OR operation, or to make the product, it is the AND operation. So in this example, if my function is three variables, is the sum of minterms 2, 3, 6, and 7, it's very important to write the variables in the right order here, so that minterms of the variables correspond to the outputs of the decoder. It means basically that the first variable in my function should go in the most significant input of my decoder, and so on. Okay, now this is minterm 2, 3, 6, and 7. These are in outputs 2, 3, 6, and 7 respectively. I have to sum them, so I use an OR gate. That's it. I have a function. Okay, if I want to use a decoder with active high outputs, then what we have are the max terms. So it's enough to have my function expressed as the product of max terms. Then I take the max terms from the output and put through an AND gate to make the product. Okay, but we can repeat this exercise because we have used here direct addition, the OR, or direct multiplication, the AND gate. But we can also use AND and NOR gates. The idea is explained in the slides, but it's like follows. If we have an expression as a sum of minterms, okay, the decoder does the minterm, which is the AND level, is the products. So we then do the OR to do the sum. But we have seen in the previous unit that a two-level circuit and OR is equivalent to two-level circuit NAND. Okay, so we can start with the solution here, but instead of using the minterms, the AND, we can use the NAND. How can obtain the complement of the minterms? By using an active low decoder, because the active low decoder simply complements the minterms. So we use an active low decoder, but we think of the outputs as the complemented minterms. So changing the AND level by a NAND level. And then to make the sum, we use a NAND instead of an OR gate. Okay. So if thinking in those terms, we just use the same connections here, but we substitute the decoder. Basically, it could be something like this. I'll draw my decoder here. We have 3 inputs, 1, 2, 3, 8 outputs that are active low, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, these are active low outputs. Okay, more or less. This order is like this, and I do 0, 1, 2, 3, 4, 6, and 7. Okay, so I have the minterms complemented here. So I take minterms 2, 3, 6, and 7, and I put them through an AND gate. These are 2, 3, 6, and 7. Okay, and that's it. We can do the other way around. If we think as a product of max terms, we can think about max terms, okay, which are some terms. So they do the OR, there are some terms, and then we do the product using an AND. But we have seen that this is equivalent to a NOR design. So if the active low decoder give us the max terms, the active high decoder give us the max term complemented, because the output is the opposite to that. Okay, so in this case we think about this design, but I make that substitution. Okay, I complement that decoder, so I go back to the active high decoder and I exchange the AND output by NOR output, so I can keep using the same output, the same numbers in the output. Okay, so it's it will be simply something like this. I'll try the drawing in a different way. See. Oh, it's not as easy as I thought. It could be great. Okay. So we have inputs 2, 1, 0. Of course, we have X, Y, and Z in this order here. This is F, X, Y, and Z. And now we have the 8, 2, 3, 4, 5, 6, 7, 8 outputs. 1, 2, 3, 4, 5, 6, and 7. So I just take the max terms 0, 1, 4, 5, 0, 1, 4, 5. Because they are complemented, then I will use a NOR instead of none. So 0, 1, 1, 4, and 5. Okay, so it will be another implementation of F. So with this, you have all the options. If you have any function, this function is the same than in the previous example. You have 4 different techniques to do that. You can think of sum of minterms and do it with a active high decoder and OR, or active low decoder and NAND, or you can think of the max terms of the function and do it with an active low decoder plus AND, or active high decoder and NOR. You have the 4 options. Now the question is, are these practical designs in reality? Well, it depends. In the old times, when many circuits were done with discrete components, it was very nice to have this option, because sometimes your function, the decoder chip will give you the minterm. So with very little gates, additional gates, you could do most functions. And the good thing is that if you change your design later, you only have to rewire some of the gates. At some point, you need to do that design and you need to change your function. For example, if you now want a function a bit different, that will be the sum of a different set of minterms, like for example 1, 3, 5, and 7, then you could just go to your circuit using discrete devices and rewire some of the connections. Okay, we eliminate these 2 connections and then we could rewire your circuit. You don't have to change everything. So in the time when we use discrete components, these are very flexible designs. Okay, and now today is not it also depends on the problem, but it's just to point out the capabilities of the decoder as a general purpose block. Okay, that's it. Thank you.